All right, let's just jump right into it. Today, we're exploring an explainer that tackles one of the absolute most mind-bending concepts in all of modern physics. We're going to look at a theory that totally challenges our fundamental perception of the universe and suggests that the reality we experience every single day might not be exactly what it seems. Before we get bogged down in the heavy math and theoretical physics, we really have to start with this totally radical question. It's a concept that completely reshapes how physicists view reality. Could it be that the three dimensions of space we move through are actually just a projection of information that's mathematically encoded on a distant, two-dimensional surface? So here's our roadmap for this explainer. We're going from the black hole paradox to information on the edge, the holographic principle, the ADS/CFT correspondence, testing the hologram, and finally wrapping up with the nature of reality. Let's get into it.
Section 1. The black hole paradox, where the mystery begins. Okay, so the very first clue in our mystery starts in arguably the most extreme environment in the universe, a black hole. When matter falls into that massive gravitational well, it seems like it just disappears from our observable universe, right? But back in the 70s, Stephen Hawking realized that black holes aren't completely black. They eventually radiate energy away. And this creates a massive paradox. You see, the radiation coming out is thermal and seemingly random. If the black hole eventually evaporates entirely, is the quantum information of the matter that fell in just lost forever? According to the absolute fundamental rules of quantum mechanics, information literally cannot be destroyed. So, if it doesn't come out in the radiation, and the black hole is gone, where did it go? This paradox kicked off a rapid, decades-long theoretical arms race, as physicists scrambled to figure out where that information actually goes. It started with Jakob Bekenstein in 1972, moved through Gerard 't Hooft and Leonard Susskind in the 90s, and then culminated in a massive mathematical breakthrough by Juan Maldacena in 1997. Let's walk through exactly how they figured this out. Which brings us to Section 2. Information on the edge. The area law. Here's the really crucial point. Jakob Bekenstein realized that black holes actually hide their secrets right on their outer limits. In normal classical thermodynamics, entropy, which is basically a measure of information, scales with volume. Bigger box, more info. But Bekenstein and later Hawking proved that gravity places a strict constraint here. A black hole's information scales with the area of its event horizon, not its internal volume. So a black hole basically represents the absolute maximum amount of information that can be packed into a given region of space. And honestly, it all boils down to the number 4. In the Bekenstein-Hawking formula, the entropy of a black hole equals exactly 1/4 of its horizon area in Planck units. Basically, this means that all the incredibly complex 3D information of the stars and gas that collapse to form the black hole is effectively encoded right on its 2D surface. Think of it like a vinyl record, a fully 3D audio experience generated by simple grooves on a flat 2D surface. All right, Section 3, the Holographic Principle, from 't Hooft to Susskind. Now, to be absolutely clear here, when physicists talk about a hologram, they are definitely not talking about glowing sci-fi light projections like you see in the movies. We're talking about a profound mathematical equivalence. A physics hologram means that the computational structure of a physical system actually dictates its geometry. The information within any 3D volume of space can be perfectly and entirely encoded by a lower dimensional boundary. So physicists Gerard 't Hooft and Leonard Susskind took that weird black hole quirk and applied it to the whole universe. The core tenets here are just wild. Basically, in a theory with gravity, physics in a 3D bulk is completely described by its boundary. The event horizon is essentially a screen storing quantum states. Localized mass has a universal entropy bound, meaning there's a fundamental limit on reality. But the craziest part? Gravity and spacetime aren't fundamental. They're just emergent properties arising from quantum information on that lower dimensional surface. Moving right along to Section 4, the ADS/CFT correspondence, the math made real. This is where the wild philosophy turns into hard, testable math. In 1997, Juan Maldacena proposed a brilliant duality that gave this principle a concrete foundation. He started with this cylinder shape representing anti-de Sitter, or ADS space. This bulk is a mathematical model of a universe with negative curvature and, crucially, a theory of quantum gravity, kind of like string theory.
Now, surrounding that 3D bulk is a 2D boundary, And on this boundary surface lives a conformal field theory, or CFT. This is a quantum gauge theory, super similar to the ones describing particle physics in our actual world, but with one absolute game changer. There is zero gravity on this boundary.
Maldacena actually proved an exact mathematical equivalence between the two. Localized information inside that gravity-heavy 3D bulk perfectly corresponds to states on the flat, gravity-free 2D boundary. It was a monumental breakthrough. It acts as this perfect translation dictionary, essentially turning a complex 3D gravitational universe into flat 2D quantum math. It was the first working model of the holographic principle.
Section 5. Testing the hologram, evidence and beyond.
So you might be wondering, how on earth do physicists actually test something this abstract? Well, the answer is modern quantum computing. Because ADS/CFT gives us this direct mathematical dictionary between quantum entanglement and space-time geometry, researchers are literally using quantum processors to test it out. By entangling specific ensembles of qubits on a boundary, they mathematically emulated a traversable wormhole in the bulk. The quantum information processing directly creates the geometric space-time connection. Absolutely mind-blowing. The implications for the future here are massive. This framework is literally our best tool yet for finally unifying Einstein's general relativity with quantum mechanics. It strongly hints that computational structure is primary to geometry, meaning space-time itself probably just emerges from quantum entanglement. Plus, it essentially provides a solid foundation for non-perturbative M theory. It's a real game-changer.
Finally, Section 6, the nature of reality, what it all means.
So what is the ultimate takeaway from all this theoretical heavy lifting? Leonard Susskind put it perfectly. The three-dimensional world of ordinary experience is a hologram, an image of reality coded on a distant two-dimensional surface. If this holds true, and decades of math like ADS/CFT strongly indicate that it does, the space, volume, and gravity we experience every single day might just be an illusion. Just like heat is an emergent property of moving molecules, our 3D universe is just the emergent property of 2D quantum information.
Which leaves us with a final, pretty provocative thought. In the math, this boundary is defined at infinity, but in our actual physical, expanding universe, if you and I and literally everything we interact with are essentially just 3D projections of 2D quantum code, where exactly is the screen? That is the next great frontier for theoretical physics.